Welcome to Chapter 3, Section 1, Complex Numbers. So something we are going to be expected to do is express them. Let's see if this one works. Expressing the square roots of negative numbers as multiples of I. Expressing square roots of negative numbers as multiples of I. So this problem stems from needing to take a square root of a number that is negative. And if you remember, previously we could not do that because there is not a number, be it positive or negative, that when you multiply it by itself, that will give you a negative number. Because any two numbers, of course, if it's positive, it's going to give you a positive. If it's negative, everybody knows a negative times a negative is a positive. So there really is not a way for us to deal with this. So we would have previously said, like, it doesn't exist. It's not real, which is true. It is complex. So I'm sure all of you guys have heard of imaginary numbers. Those are ones with an I. So since there's essentially no way to deal with a negative square root, that is why we introduce I. So notice here, I'll maybe do some yellow. So notice here that I is equal to the square root of negative 1. This is the process of getting that square root. So what happens is you would take that negative out on the inside by just doing a negative 1. And by the properties of roots, you can actually break that up so that you get the square root of 25 times the square root of negative 1. And since the square root of negative 1 is I, that is what we get. We get 5I. Now, it is not okay to put the I first. So it's not I5. It is 5I. And that's the way it always is. And if you do higher level math, that is definitely something that you will get corrected on. So when a number involves I, we call it a complex number. So when you have a complex number, it will have a real part and an imaginary part. So this is the form of a complex number, A plus BI. So A is your real component. BI is the imaginary component. Notice that when you have no imaginary part, so when your B is 0, you just get a real number, which is, that's what's supposed to happen. When you do not have a real part, you have a purely imaginary number. So there's no real component of that at all. It is just something multiplied by I. Notice that if you do have a real component, it will be some real number will be added to your imaginary number. And that real number, the A, must come first. So that if I had an imaginary number 5 plus 6I, we would not write it 6I plus 5. That's not how we would write it. This would be it. We also would not put that I first. So plotting a complex number on the complex plane. I'll go ahead and use yellow for this one too. The pink can be a little hard to see through. So because of the imaginary component, we cannot plot complex numbers like we do other numbers. So now instead of an x and a y, you have to have your x-axis will be your entirely real axis. So that's all your real numbers, every number you can count. Your y-axis now becomes your imaginary axis. So that's going to be your number that is multiplied by I. So here, for example, we have -2 plus 3i. So notice that we've gone over to -2 on the real axis. And now we go up, +3 on the imaginary axis. And that gives you the number -2 plus 3i. So adding and subtracting complex numbers is also something that we can do. And this is relatively easy. It's intuitive. That means that if you already know how to add and subtract things, you would be able to guess what you would do. So for adding, you can just add them all together. You can just drop the parentheses and add them all together. Now for subtracting, I recommend you keep the parentheses until you have distributed that subtraction sign to everything. And then you just combine like terms and write it in the form a plus bi. Now we use these as an example. Notice that I just went ahead and dropped the parentheses, rearranged it to combine like terms right here. And then I simplified those like terms. And I did the same thing here. I went ahead and distributed that negative. I rearranged it to have the terms together, and then I combined them for the final answer. Multiplying complex numbers. So we can multiply complex numbers by any real number. It doesn't matter. And this one is really intuitive also. Of course, you would just distribute the real number to everything. But when you multiply two complex numbers or purely imaginary numbers together, something special happens. And it pertains to the i's. So notice that when we have 2 minus 3i times 9 plus 4i, we are going to multiply everything. And I just wrote it in maybe a bit of a different notation here. So what I did was I took that -2 and I'm going to multiply it by this whole thing, and that gives me this term. And then I'm going to add this -3 multiplied by this whole thing again. And sometimes I may write it like this, and that's just so that if somebody is a little confused by me immediately jumping to the next step, we can go back and see what's going on, especially with that negative, because that's very confusing sometimes. And I mean, it can literally just get lost. I myself have dropped negatives, and the consequence of that is the wrong answer, which is unfortunate. So now we've multiplied all these out. We get our 18. Notice we have to combine these terms. And here's what we get. I squared. This looks an awful lot like a quadratic equation, but it will not when we are done. So you might be thinking, well, I squared. What does that mean? So notice here that I squared is the negative square root of 1 times the negative square root of 1. And when we combine those, we have squared the square root of -1, which just gives us -1. As a consequence of that, we can see that in what we were doing earlier, this I squared term becomes -1. So now our -12 has turned into a +12, and we combine it with the 18 to give us 30 minus 19i. Let's see how long. Now notice this table right here. This is our table for powers of I. I included I to the 5th, but notice that they repeat after I to the 4th. So here I equals the square root of -1. And what I mean by that is when we have I, we get the square root of -1. I squared is the square root of -1 times the square root of -1, which is -1. Because remember, anytime you multiply square roots, it is whatever is inside the square roots. I to the 3 equals, we're going to break this down into I times I squared. And here is an important rule for variables. And then another really important one would be a n times m equals a n times m. Those are rules that you'll need to know for this. So we broke that down. Remember, we can do that because they'll add to 3. So 2 and 1 add to 3. So we're going to have I times I squared, and I squared is -1, which gives us negative I. I to the 4th is going to be I to the 2nd times I to the 2nd, and that's because they both add to 4. And that gives us -1 times -1 is equal to 1. And then for I5th, we can break this down into I times I to the 4th. And that equals I times 1 equals I. And then that just starts back over. So for example, I to the 6th can be I squared times I4 because they add to 6. And then you would get -1 times 1, which is -1. Which goes down to the next one. And then they'll just keep rotating in order like that. So now dividing complex numbers. And keep this table in mind because we're going to be using it again later. So dividing complex numbers. So in order to divide complex numbers, we're going to have to use something called a complex conjugate. So what that means is that the complex conjugate is the opposite middle sign. I don't know. So here it's the same complex number, but with the imaginary component sign switched. Notice this. Notice the middle sign was switched. So if we had a plus bi and we needed the complex conjugate, we would get a minus bi. That's what we would use. Here, if we had a minus bi, we would use a plus bi. So here we're going to use this guy as an example. So the complex conjugate of the denominator is 4 plus I. So we're going to multiply the top and the bottom by 4 plus I. And I'm just going to reference here. We can do that because that means as long as we multiply the top and the bottom of the fraction, we are essentially just multiplying by 1, which would be allowed, right? Because these here would cancel out to be 1, so you're just multiplying the whole fraction by 1. But we're going to use a special property. So when we multiply these with opposite signs on the imaginary part, it will make the imaginary part disappear. So notice the top, we just foiled out like we do for regular complex number multiplication. For the bottom, we did the exact same thing. So you will get I in the top, which is totally fine, but you will not get I in the bottom, in the denominator right here. Notice that when we had opposite signs, these two terms canceled out so that we were left with negative I squared. And I squared is -1, and we can see that from the chart. So it really just equaled +1. And then we rearranged, 8 minus 5 was 3. So we would have originally had something like 3 plus 22i divided by 17. And then we just broke that down into pieces. 17 on the bottom of both. Now simplifying powers of I. This is where we will use our table above. So notice there is not really one correct way to do this. I did it, 3 different ways. It doesn't matter because there's no right answer. There's no right path, but the answer should be the same. And notice that my final answer on all of them is the same. So what you do when you have very large powers of I is you break it up. And you remember these rules? They're going to apply here. So if I had I 177, I could break that up into I 100 and I 77 because those exponents will add to 177. And that's right here. Now, if you notice the third one, I used the other property, the property of multiplication. So 59 divided by 3 is 177. So that allowed me to reduce it down to the power of 59. Now the reason I can pull this negative out is because this is odd. You pull the negative out. If the power is odd, you pull the negative out, like right here. And here I just broke this up into 20 and 39 because 20 and 39 add to 59. But notice I did pull out that negative. So that's what I did, and I carry the negative along until it would cancel out with here. I pull out another negative because this is to the negative. This is to an odd power, so I can pull the negative out all the way here so that it cancels. So you get a positive. And now, and of course that all, break it all down. And this is the easy part. When you get down to something simple, it can be all of these will add to 13. And that's how I broke it up. And I broke it up with the maximum being I to the 4th because of this property up here, since I to the 4th equals 1. And that allowed me to keep it very simple here. So notice for this first one, we're going to go back here. And I just keep, going down the line, canceling everything out. And here, this is what I want to point out. So notice for number 3, I had an odd power, so I was able to take out that negative. Well, here I have an even power. So that means my negative goes away. It just goes away completely. So that would be the same. -1 even is going to be the same as just 1 to that same even power. And if we had -1 or negative anything to an odd power, it would equal negative the positive number to the odd power. You can pull that out. So now let's look at some examples. We will go over these two here, and maybe I'll save the other ones for something else. So for number 2, 6 minus 5i minus 10 plus 3i. And here I have to distribute that negative, so it's going to become -10 minus 3i, which will simplify to 6 minus 10 if we group the terms, minus 5i minus 3i, which will give us negative 4 minus 8i. And that's how we would leave it. It's not necessary to like factor out the 4 or anything. We could, yeah, there'd be no point in doing that. So this is what the answer would be. So number 4, this is where we use a complex conjugate. So our complex conjugate, remember, it's the opposite sign of the imaginary part. So this would be 2 minus I. And we're going to multiply those out. So I guess it would be easiest to look at if we had parentheses. So now 2 times 2 is 4. And then we're going to have negative 2i and another negative 2i. And then plus I squared. And then we're going to have 4, a negative 2i, a positive 2i, and a negative I squared. So that's going to give us 4 minus 4i plus I squared divided by 4 minus I squared. Now, if you remember what I squared is from the chart, that is very helpful. But if unfortunately you can't remember what I squared is from the chart, you can always remember that I is the square root of negative 1. So therefore your I squared is just the square root of negative 1 squared, which is negative 1. So that gives us 4 minus 4i. This equals negative 1, so that's minus 1. And then this equals negative 1, so that's plus 1, because the signs will switch. So now you have 3 minus 4i divided by 5, which you can break up into 3/5 minus 4/5 I. Okay, so solving the following equations over the complex number system. Let me head back to the notes really quick. This one has to do with this. So, where we are now in pre-calculus, it is assumed that you know the quadratic formula and that is one of your go-to things to solve a quadratic function. So that is x equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. I'm just going to put that right there for you. Surely this looks familiar. If it does not look familiar, we will be going over it again. So, but at this point, the book, does make the assumption that you guys learned this in Algebra 2. So don't worry if you looked at, the examples and you were immediately like, hey, I don't remember covering this when we were talking about complex numbers. But that's what the book assumes. So I'm going to take one of these and I'm going to show you kind of what is going on. There we go, equals 0. So this is in the form ax squared plus bx plus c equals 0. So remember to solve, we use x equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. And remember previously that if you have solved these in Algebra 2, if you got anything that was negative, if b squared minus 4ac was negative, you really didn't have a way to solve it. With complex numbers, we do. So here, I know my a is equal to 1 because that's what's imaginary, is right there, little 1. It's invisible, the invisible 1. famous invisible one. B is -4. And C is +5. I covered it up, but that is a plus sign. So now we're going to go negative, and B is -4, plus or minus. And I like to write the square root symbol after I've written everything because sometimes it gets really long. So I leave a little space. -4 squared minus 4 times A is 1, C is 5. And then I'm going to write that square root. And then I'm going to divide this by 2. A is 1. So now I am going to keep going. So -4 is +4, plus or minus. -4 squared is just 16. 4 times 1 is 4. Times 5 is 20. All that under a square root. And 2 times 1 is, of course, 2. And I'm going to keep going. 4 plus or minus 16 minus 20 is -4 divided by 2. And oh no! See, we got this guy, the negative guy. And previously we could not deal with that. We were like, well, you know, that's not my problem. But, you know, there's no solution within the domain. Now there is, guys. It's getting real. Now there's a solution. You've matured enough in your mathematical career that we can solve this because we learned I. So I'm going to break it up, and it's -1 times 4. And then remember my rule, A times B, all under whatever root, is going to equal those same things broken up under that same root, you know, multiplied together. So that's 4 plus or minus -1, 4 divided by 2. Remember what the square root of -1 is? Give you a second. It is I. Not me, but the imaginary number I. And what is the square root of 4? That's 2. Now, notice, this is how I would usually do it, but I do note that now I have to rearrange it because I can't come first. So 4 plus or minus 2i divided by 2. And now I can break these up. And we're going to take this guy over here to become 4 divided by 2 plus or minus 2i divided by 2, which gives us 2 solutions. 4 divided by 2 is 2. And then we take plus 2 divided by 2 is 1. And then we're going to take, again, 4 divided by 2 is 2. And we're going to take that bottom sign, the minus. And now 2 divided by 2 again is 1, so we get I. So x equals 2 plus I, 2 minus I. Now, one thing I want you to make note of here, because it will come up later when we talk about polynomials, notice that we have a complex number and its conjugate. Oh. Remember, the conjugate is the opposite sign. I know some of you probably already noticed that, wow, they look kind of really similar. Well, that absolutely will come up later. Absolutely will come up later. So if you notice that, great job. You're thinking along the lines of other great mathematicians. So yes, keep that in mind because this will be an important theorem later on. So that covers 3.1. complex numbers. I will see you in the next one.